Hey guys, let's continue with our lectures on integration. Okay, so we are starting integration today, and first of all you must know this thing, and I have told you again and again that integration and differentiation are reverse operations. Integration and differentiation are reverse operations. So when we differentiate anything, we can go back to the original function using integration. So that is what integration stands in the basic version. So for integration we need to calculate the integral. Just like in differentiation we calculate the derivative, here we calculate the integral, which is in turn called the antiderivative. It is called the antiderivative. Right, and the integral of the antiderivative geometrically, it represents the area under a graph. You should it should be very well understood that there is a geometrical meaning of every calculus function. Like if we talk about the differentiation of the derivative of a function, it represents geometrically the tangent of any equation, the tangent of any graph at x1 if you find the derivative of that function at x1. Similarly, the integral means it represents the area under a graph geometrically. So what is representation? The representation stands for an elongated S. The line here we have shown, this line here is an elongated S, and it is fx into dx. Right, this is the representation. Now let's understand the concept behind it. Okay, so the concept. Let's say we have a function here, and the function here stands for f of x. Y is equal to f of x. Now, we have tried to divide the function into certain rectangles. Like we have taken the function from starting from x1 here to ending up to x2 here. So, we divide the function of the graph into certain rectangles. Now we can see that at x1 we have a rectangle of this much height. Right, we have a rectangle of this much height, and at this position the value of the function is fx1, and what we have done is we have taken the width of the rectangle as same as h, and we have taken h in that way such that the last function, the last point x2 is equal to x1 plus nh, right? So that this satisfies this equation, h is equal to x2 minus x1 upon n. So we have divided the area under the graph into n portions with same width of x2 minus x1 upon n. So for calculating the area, an approximate area, I can say that I can add the areas of all these rectangles. So what is the area of the first rectangle? The area of the first rectangle would be f of x1 into x1 plus h minus x1, which is equal to h. So that I have written here, h into f of x1. Similarly, if I calculate the second one, I will get x1 plus 2h minus x1 plus h into f of x1 plus h. And similarly, I have put it here in the second term. So when we add these all terms together, we'll get this summation here, that is h into sigma k equal to 1 till n f of x1 plus k minus 1 into h. You should note that k minus 1 bar stands for k minus 1 in brackets, like it is together rather than minus 1 and h being together. Right. Now we see that this gives an approximate area of the graph rather than giving us the actual area of the graph. So for making it the actual area, we need to minimize the width of the rectangles, because if we minimize the width of the rectangles, let's suppose I have taken a point here. And I take a much smaller width graph, much smaller width point or a distance. Okay, right here, like this is a little smaller. So we can see that the approximation reduces and will reduce till 0 if the width is taken more and more smaller. So when we take a very very small width, around infinitesimally small, we say we have taken a width of dx. Right? We say we have taken a width of dx. And if this point is x here, I can say that this then be equal to summation of f of x into dx. Right. Now what does the dx signify here? Well, the dx signify is when I take an infinite number of rectangles here. That is, here what I do is I limit n approaching infinity h. So this will be the new h, or this will be equal to dx. So that the dx will be equal to n approaches infinity x2 minus x1 over n. Right. So you can say that when n is equal to infinity, dx has approached equal to 0, is approaching equal to 0. So we get a more smaller area, like more smaller approximation for the area, and thus we get the area under the graph. So what we say here, first we take the area of the graph, then we differentiate it into rectangles, and then we integrate all the rectangles or sum up all these rectangles. This is the concept of differentiation.